What is the slope at a point on a curve f of x? What is the area under f of x? Derivative, slope, integrals, area. To find the slopes of tangent lines on curves, note that the slope of the secant lines approach the slope of the tangent lines. To find the areas underneath functions, note that the area of the rectangles approach the area of the trapezoid when we have many thin rectangles. Both slopes and areas depend on approaching, that is, limits. Absolute value x for x not equal to 0, absolute value x for x not equal to 0, 0.5 for x equals 0. What did the values of f of x approach as x approaches 0? These f of x values approach 0 as x approaches 0 on either side, but x is not equal to 0. Visually, we can consider arrows that trace the curve on either side, or a red box of decreasing height and the blue box of decreasing width. The f of x values approach 0 as x approaches 0 on either side, but x is not equal to 0. Limit as x approaches 0 of f of x equals 0. Note how limits could exist in general. Limit as x approaches a of f of x equals f of a. Limit as x approaches a of f of x exists, but f of a does not exist. Limit as x approaches a of f of x does not equal f of a. Consider limit as x approaches a of f of x as a double-sided limit here, where both limit as x approaches a from the positive, f of x, approaching a from the right, equals limit as x approaches a from the minus f of x, approaching a from the left. F of x equals absolute value x over x, which equals this. What do the values of f of x approach as x approaches 0? As x approaches 0, the f of x values approach minus 1 from the left, but 1 from the right. The limit as x approaches 0 from the negative f of x equals minus 1 does not equal limit as x approaches 0 from the positive f of x equals 1. The f of x values don't approach any one number as x approaches 0 from either side. The red box cannot decrease in height as blue decreases in width. The double-sided limit does not exist, but each one-sided does exist. Limits. Limit as x approaches a of f of x equals L if and only if limit as x approaches a from the minus f of x equals L equals limit as x approaches a from the positive f of x. The intuitive idea of the limit is that we can make the values of f of x as close to L as we like by making x close enough on either side of a, but x is not equal to a. We say the limit of f of x as x approaches a equals L. If the limit is one-sided, then we say left-hand limit or right-hand limit. Algebraically, we can show that limit as x approaches 0, absolute value x equals 0. We start with the function, make it piecewise, and show that both the left and right limits are equal. Limit as x approaches 0, absolute value x, and recall that absolute value x equals this. Limit as x approaches 0 from the negative absolute value x equals limit as x approaches 0 from the negative minus x equals 0 equals limit as x approaches 0 from the positive absolute value x equals limit as x approaches 0 from the positive x equals 0. Algebraically, we can show that limit as x approaches 0, absolute value of x over x, does not exist. We start with the function, make it piecewise, and show that the left and right limits are not equal. Limit x as it approaches 0, absolute value x over x, and note that absolute value x over x equals this. Limit x approaches 0 from the negative, absolute value x over x, equals limit as x approaches 0 from the negative minus 1 equals minus 1, does not equal limit as x approaches 0 from the positive, absolute value x over x, equals limit as x approaches 0 from the positive 1 equals 1. Limits. Nuance. Note that two functions could not have limits, but their sum could. For example, here. So be careful when it comes to combinations of functions and intuitive limits. Below, see what happens to the values of f of x as x approaches 0. The arrows wouldn't approach the same value. The red box couldn't get short. The limit does not exist when f of x does not approach a number L, no matter how close x is on either side. No two-sided limit, oscillation, and plus and minus infinity. But we can use the notation of limits with the infinity sign. Asymptotes. Consider the various combinations of limit as x approaches a f of x equals L, both two- and one-sided, if a and or L would be either positive or minus infinity. Vertical and horizontal asymptotes. Vertical asymptotes, x equals a, are when f of x approaches positive or minus infinity as x approaches a in some way, often when a non-zero is divided by a zero. Horizontal asymptotes y equals L are when f of x approaches L as x approaches positive infinity or minus infinity. 1 over x, 1 over x squared, x cubed, minus x to the power 3. Various limits. f1, f2 have a vertical asymptote at x equals 0. f1, f2 have a horizontal asymptote at y equals 0. Ln x, e to the x, tangent x, arctan x. Various limits. f3 has a vertical asymptote at x equals 0. f4 has both at x equals minus pi over 2 and x equals pi over 2. f5 has a horizontal asymptote at y equals 0, and f6 has both at y equals minus pi over 2 and y equals pi over 2. Algebraically, we can show that limit as x approaches 0, 1 over x does not exist, and limit as x approaches 0, 1 over x squared equals infinity. We start by finding the left and right side limits and see if they're equal. Note that pos means tiny positive and neg means tiny negative. Limit as x approaches 0 from the minus 1 over x equals 1 over neg equals minus infinity. Does not equal limit as x approaches 0 from the positive 1 over x equals 1 over pos equals positive infinity. Limit x approaches 0 from the negative 1 over x squared equals 1 over neg squared equals 1 over pos equals positive infinity equals limit as x approaches 0 from the positive 1 over x squared equals 1 over pos squared equals positive infinity. Algebraically, we can find the first positive vertical asymptote of tangent x with tangent equals sine over cosine being non-zero over 0, which is visually this. Note that cosine x equals 0 when x equals pi over 2 plus n pi, and sine x equals 0 when x equals n pi. We have the following. So, x equals pi over 2 is the first positive vertical asymptote of tangent x. Rational-ish functions. To find the asymptotes of rational functions, technically we divide all terms by the highest power in the denominator and evaluate the limits. For us, we use the ratio of the terms with the highest exponents, since they matter more than the other terms. Pos means huge positive. We have the following. First case. Generally, the limits as x approaches infinity or x approaches minus infinity may differ due to coefficients exponents. Second and third cases, the limits are the same as x approaches positive or minus infinity. With radicals, the terms with the highest exponent still matter the most, but we might have different limits as x approaches infinity or x approaches minus infinity. We have the following. Algebraically, we can show that limit as x approaches 0 arctan 1 over x does not exist. We start by finding the left and right side limits and see if they're equal. We need a substitution to make our composite function into a simple one. Let t equal 1 over x. As x approaches 0 from the negative, then t approaches negative infinity, and as x approaches 0 from the positive, then t approaches infinity. Limit as x approaches 0 from the negative, arctan of 1 over x becomes limit as t approaches minus infinity of arctan t equals negative pi over 2. Does not equal limit as x approaches 0 from the positive arctan of 1 over x, which becomes limit as t approaches infinity arctan of t equals pi over 2. Algebraically, we can show that limit as x approaches 0 of arctan of 1 over x squared equals pi over 2. We start by finding the left and right side limits and see if they're equal. We need a substitution to make our composite function into a simple one. Let t equal 1 over x squared. As x approaches 0 from the negative, then t approaches infinity. And as x approaches 0 from the positive, then t approaches infinity. Limit as x approaches 0 from the negative, arctan of 1 over x squared becomes limit as t approaches infinity, arctan of t equals pi over 2 equals limit as x approaches 0 from the positive, arctan of 1 over x squared becomes limit as t approaches infinity, arctan of t equals pi over 2. For one-sided limits, like limit as x approaches infinity of sine 1 over x, limit as x approaches minus infinity, sine 1 over x, and limit as x approaches 0 from the negative of e to the 1 over x, be careful with how we approach. Below, with t equals 1 over x, note that we need positives or negatives when t approaches 0. When x approaches infinity, then t approaches 0 from the positive, And when x approaches minus infinity, then t approaches 0 from the negative. When x approaches 0 from the negative, then t approaches minus infinity. Limit as x approaches infinity sine 1 over x becomes limit as t approaches 0 from the positive sine of t equals 0. Limit as x approaches minus infinity sine 1 over x becomes limit as t approaches 0 from the negative sine of t equals 0. Limit as x approaches 0 from the negative e to the 1 over x becomes limit t approaches minus infinity e to the t equals 0. We can find limit x approaches infinity x squared minus x, but we cannot substitute positive or minus infinity. We need to manipulate, factor, make into a fraction, etc., and consider pos, huge positive, and neg, huge negative. Limit x approaches infinity x squared minus x equals limit x approaches infinity x minus 1 equals pos times pos equals infinity. Or we could have this. We can show that limit x approaches infinity sine x or limit x approaches minus infinity sine x does not exist. The values oscillate between -1 and 1 infinitely often and don't approach any definite number.